All right, thank you for being here. So it's a pleasure to have Anuran, who is, as many of you know, is in his second year of his PhD in the computational biology graduate program, to talk in details about some of the aspects of AI and deep learning, specifically involving neural network models, that I kind of very superficially went over on in the colloquium I gave. So I can't think of anybody better suited than him to actually speak on that, because Anuran has been working for like something like 1.5 years to 2 years on neural networks, initially on how to train deep neural networks using various algorithms, but then eventually he also has covered a lot of the physics of it. And he has very painstakingly gone through the key papers behind this physics revolution of neural networks. And today, in the first part of the talk, he'll be talking of like from McCulloch-Pitts neuron in 1943 to the era of Hopfield in 1982. And in the following talk on Tuesday, he will be taking us on to Hinton and all the way up to large language models of today. So, Anuran, without any further ado, let me invite you to get the talk.
Thanks, Siddharth. Hi. So yeah, today I'll mostly cover till start with how people have been trying to think of brain or information processing of brains. So, well, artificial neural networks are essentially philosophers, mathematicians, biologists attempt to computer scientists attempt to sort of understand how brain process information. So the basic unit of any nervous system is a neuron, right? So which has a particular cell body that processes or that sort of says if it fires or not after taking in input from the dendrons. So there is information or activity coming in from the dendrons, and if it satisfies some constraints, then it sends over its own activity to its next neuron. So brain is essentially a connection of these neurons, which so this is the cell body, right? So you can actually think of it as a binary threshold unit. So as Sitabra pointed out in his talk, that George Boole, sort of how he came up with Boolean algebra was because he was sort of thinking about how do you logically process information, right? So that was like the beginning, right? So in around 1943, McCulloch and Pitts, they came up with the first abstract model of a neuron, which is a binary threshold unit. So the unit essentially takes in input from all the other units. So x1, x2, let's say, are the units. And so they're connected with some dendrons and their other, like, wherever it's coming from their axon. So it has a particular strength associated as well. Right? So the amount of input that this particular cell body is getting is essentially the sum over of all the activity of the neurons that it's connected to or the units that it's connected to, right? So this is essentially 1943 McCulloch and Pitts abstraction of what a neuron could be. So the amount of input received is from all the other neurons multiplied with their corresponding weights. And then it checks, this particular unit checks if it's above a certain threshold. If it's above the certain threshold, is it visible, everyone? Bigger? Sorry. Um, well, or you can come closer. So, so these are essentially WIs. So W1, W2, WN, and these are the activity of other neurons which it's connected to. And that is sort of being somewhat summed over in this particular neuron. And then the neuron checks if it's above a certain threshold, it fires. If it's not, then it doesn't fire. Right? So what McCulloch-Pitts showed is this sort of an architecture or this sort of a unit can form any logic gate operation, almost any logic gate operation. So for that, let's just walk through how one can make an AND gate and an OR gate with this. So this is McCulloch-Pitts, who showed that you can abstractly think of a particular neuron as a binary threshold unit. So this sends out uh, the activity of the neuron based on this. If it's above the threshold, it sends off +1. If it's not, it's -1. So let's try and construct an AND gate for a demonstration with this particular type of neuron. So generally Boolean algebra is with zeros and ones, but I'm just choosing -1, 1. It doesn't matter, it's just a change of threshold. So AND will essentially look like this, right? So if there's any question or if you think I'm making a mistake, please stop me and ask me a question. So this is the logic gate that we're going to try to make with these binary thresholds, right? So we have two inputs, x1 and x2, coming from the input, like, and our y is the one which is going to make the add. So if we allow a +1 interaction over here, and the threshold of this be minus, we're going to think about that. Let's construct it on the way. So how does the input space look like? The input space, that is x1 and x2 space, looks something like this, right? x2, x1, and you have these four possibilities where these three are off, right? Whenever the input is over here, then y should not fire because it's an AND gate. And whenever it's above, like both of them are on, that is +1, +1, then y should fire, right? So we sort of need the threshold to be somewhere around here, so that whenever the input is above this particular threshold, the neuron fires. So what will y look like according to this logic? W1, which is 1, x1, plus W2, which is 1, x2. And so this is essentially a plane in 2D, right? And the equation of this plane is x1 plus x2 plus 1, right? So the threshold essentially has to be -1. If I think of the threshold as WIXI minus theta, the total input received. So y is equal to sum over I, WI, XI minus theta. So you can essentially see that if x1, x2 is -1, then this is -1, -1 plus 1, and it is negative, so it doesn't fire. It's below the threshold. So I put the threshold here, so we're just going to see if it's below 0 or above 0. If it's +1, -1, that is these two scenarios, then the +1, -1 cancels out and it's, yeah, here made a mistake. It should be -1, right? So, right, so +1, -1 cancel out, there you have a -1, and so the y neuron doesn't fire. And it will only fire only if +1 and +1 is there. So +1, +1, 2, -1, y equal to +1. So this will give you an AND gate, binary neurons. Similarly, we can construct a OR gate with this binary threshold unit. The OR gate input space looks something like this, right? The decision boundaries sort of has to be here. So this is on. Like the y has to be on when the input is over here, and for the OR gate, the y has to be on if the input is over here, right? So this is x2, x1. So how does it have? How should it look? It should sort of look like, so we have this y unit, and it's receiving input from x1 and x2 with a weight of +1. So y should have to be x1 plus x2, and so whenever it's the OR truth table is +1 in these two and -1 when both of them are -1, right? So I'll just quickly write it maybe. right? So the decision boundary has to be sort of here. And this will give you, so the threshold of this y unit has to be minus. And yeah, please guys, if you see if I'm making a mistake and you please point it out. So this will essentially give you an OR gate, right? Now, what we are doing over here is we are essentially know how what the input and output has to be, and it's very simple to work out what the weights have to be. So it's pretty straightforward to do. But yeah, here we are thinking only in terms of Boolean. So plus one minus plus one zero, plus one minus one. Yes, yes.
The weights, the W's, they can be anything, right?
The W's can be anything. Yes.
So I was just thinking, if you wrote y is equal to minus x1 minus x2 plus 1, then that is an AND gate.
NAND gate.
Yeah.
Correct.
And that's a universal gate, so you can make anything out of an AND gate.
Well, we'll see that there are particular types of gates which cannot be made with this simple prescription.
I see. Well, okay, so then my question was, supposing you just flipped it, y is minus one, x1 minus x2 plus 1 with the same threshold.
Yes.
Then
Then our
isn't that an
input
AND gate?
space will look like,
So it will be a 0 if they're both inputs are both plus 1. I mean, it'll not fire if they're both plus 1, and it'll fire if at least one of them is minus 1.
right, it will fire only here.
So that's an AND gate.
That's a NAND gate, yeah.
But the NAND gate is a universal gate. You can construct anything out of NAND gates. You can construct or no.
Can we construct XOR? I'm moving forward in the
Yes.
story. We can construct XOR.
By layering NAND gates, you can construct anything.
I see.
Uh,
So, what do you mean by layering?
For example, just receiving voice, right?
Okay, okay. Hmm.
So it is uh, all in one, right? That's what.
Eh, yeah, yeah. I see.
So you are getting which one is that NAND gate?
I mean, you can technically make an AND gate with this. Okay, I need to read up on that a bit. Okay, so here what we are essentially doing is we are putting the weights by ourselves, right? It's not that the network is learning on its own. That's no. In McCulloch, what they showed is they were thinking of neurons like this, and what he showed, like what he sort of abstracted out is, this is sort of like a positive contribution from this to this, and well, let me draw another over here. This is sort of like a not contribution. So when they were McCulloch-Pitts, when they were making this abstract model, they did consider not in this form. So I'm not sure. Like W's should be allowed to be negative. Um, all right. Shall I continue? Uh, so yeah, here we are sort of putting the weights on our own, and we would like, so given an input and an output, or given a truth table, we would like the network to sort of learn the weights on its own, right? So this was sort of done by two set of groups, I think. One was Widrow and Hoff, advisor and grad student. They came up with a gradient, the first gradient descent algorithm. So what they said is consider the desired input to be y star. So here replace this with y star, and the y. So this is desired. That will essentially give you the Boolean table. And y, the output from the network, and you want to construct the weights or make the network learn the weights such that this particular cost, the first mean square error, is minimized. So this was Widrow and Hoff, and what in 1960, I think. And what they said is you can sort of um, change the weight. So delta Wij, eta being the learning parameter, and so there's a minus dou C dou Wij. So this was the first gradient descent algorithm recorded, and what this gives you is if you just do some calculation, you'll
Sorry for making a wrong statement. You can construct NAND gate, but to construct XOR, you have to layer two NAND gates, and so therefore you will have to create a hidden layer. So even though yes, it's possible to get XOR from NAND, but you can't escape making a hidden layer. So that was the logic. Right, correct. So the reason you can do NAND gate but not XOR is NAND requires only one decision boundary, and you can do that using an input layer and output layer. But XOR requires two decision boundaries, and so for that you need a hidden layer. Yeah, no, because you can't train it using the training algorithm that these guys were using. That's the problem.
Yeah, so the training algorithm that Widrow-Hoff and Rosenblatt as well came up with requires, as we'll see, so it essentially says minus eta dou C. So you go along the negative, the gradient of the cost, right? So what you realize is delta Wij essentially becomes, so you put the cost inside, y star, there's a half as well, y star minus y whole squared of, right? And so what you realize is this y over here is actually the input received from the other neuron. So this y is essentially sum over I wi xi, right? So only I was right, j, no j, right? There is only one output, wi xi. Yeah. So what you realize is only the xi will come out, the others will become 0. So you end up with wi is equal to, so to learn it, you require the desired value at the output, the value that you're getting, and the input, right? So you need the desired as well. So yeah, and Rosenblatt also gave a similar argument, but heuristic. So this can, yeah. So we are not considering threshold, like I didn't really focus on thresholding because you can always imagine a scenario where this node is essentially connected to another node which is always minus 1 and it's connected to 1. Essentially, you're writing Wixi, right? So let's Wixi, and let's say this is the x0 and this is the w0. So I goes from 0 to 2. So if you have this Wixi minus w0 and w0, so instead of w0 equal to plus 1, then you essentially get minus W0, which is minus theta. So you can replace a threshold by connecting it to a unit which is always on. Is that, yeah? Yeah, here, so that was the difference between Widrow-Hoff's model and Rosenblatt's model. Rosenblatt, very good point. So Rosenblatt essentially considered the final output of y, but Widrow-Hoff considered sum over Wixi, just this part, before the threshold. So that was the key difference between Rosenblatt and Widrow-Hoff. So in Widrow-Hoff's derivation, what they did is they used this as the uh, obtained output, not after passing it through the step function, right? Yeah. So in case of Rosenblatt's case, if you put the threshold, which is a step function, there is no gradient over here. So you need something like a smooth. Yeah. So they didn't really think of these smooth. Yes. Yes. Right. 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 I see what you're saying. Okay, because you need the thresholding to. Yeah. So in with this sort of a learning algorithm, you can sort of get these desired gains, but and well, the media got hooked onto it, and there were a lot of predictions that we're gonna. So essentially, what happened is around 1969, what they showed, Linsky and Papert, is that you can get uh, this sort of a learning algorithm will work only for certain class of problem, which are called linearly separable problems. So, and it's kind of so the example that they gave, and this is famously called the Zor problem. Yeah, so what's the truth table of Zor? Um, so plus 1 gives you minus 1, plus 1 minus 1, plus 1. Right? So if you look at the input space, what it requires so this is x2, x1. So there are two areas where it's not. So it will only turn on when the input is above a certain threshold and below a certain threshold. Right? So now the problem with this sort of formalism is this has only one threshold, right? So if you go above this threshold, and it will give you on, but there is no other threshold to turn it off again, right? So because you see, this is the equation of a straight line, and straight line is essentially gives you a single line, above which it's on, below which it's off. But what XOR requires, it requires two lines. One, so these are called decision boundaries. It requires two decision boundaries, above one of them, it's on, below one of them, it's off. So if we try to think about yeah. Any questions? So if you try to think about this is sort of like the OR gate, and this is sort of like the NAND gate, right? So you need a OR and a NAND will give you XOR, right? So we can actually think how we can work out how hidden layers actually get over this problem and uh, give you a XOR gate. So we have this X1 and an x2. And let's consider the hidden nodes h1 and h2, right? So let's say h1 tells you the OR, right? So h1 is equal to x1 plus x2 plus 1. So this is essentially encapsulates the OR decision boundary, right? And the h2 essentially encapsulates the NAND decision boundary. So minus x1 minus x2 minus 1, right? So essentially this is connecting, it's sending information with strength of minus 1. This is sending an information of strength plus 1. This one has a threshold of minus 1 and this one has a threshold of plus 1. And so this over here you have a OR and this over here you have a NAND. So once you have this, so what are they doing to the input space? They're essentially dividing the input space into two halves, right? This, so these are the four cases. So the first one, this is the OR, and the other one here is the NAND, right? So what all you need to do is essentially say AND of these two hidden layers. Once you have an AND of these two hidden layers, so plus one, and so y will essentially be h1 plus h2 minus 1. So this can give you a XOR. So this sort of shows you need hidden layers to put more number of decision boundaries, more than one, on the input space. So essentially, if you put another hidden layer, you get a question. Yeah, yeah. Sorry, where? This one? No. That's what he was pointing out. Right. So you need the boundary. The boundary will tell you where it is 0, where the input received is 0. If you're above the boundary, you have positive. If you're below the boundary, it's negative. But the units themselves are binary. So if it's above 0, it will be plus 1. If it's below 0, it will be minus 1. So what they did over here, I think Woodrow and Hoff, is they didn't put the thresholding, the step function. But that, as Rahul points out, will not. It's essentially sends over linear function. It's a linear function. How can I get a linear function with? How can I get the XOR gate? Because you see, if you're above a certain value, you will be positive. You cannot become negative. And if you're below a certain value, you'll become negative. But what XOR requires is it requires you to be negative, become positive, and then again become negative. Right? Hmm. Hmm. What? Yeah. So I have. Okay. So y is sort of given as yeah, and right, yeah. I see. Okay. So, but for that you will require two thresholds as well, right? Where it's going from +1 to 0. Yeah, right. Okay. Huh, I mean, but we're using this simple McCulloch-Pitts architecture. You can only have one threshold. Yeah. So this will be theta equal to +1. Yeah. Yeah. So we're over here. Yeah. So it'll be -1. Yeah, it's below, way below the step function, way below the step. No, no, H2. So H2 goes inside that step function, and then you get the value of the node. This is the input that I'm getting, the amount of input that each of them are getting, and then it goes through the threshold function. So it's this that I'm writing. Then it goes through the threshold function, and if it's greater than 0, it takes +1. If it's less than 0, it takes -1. Yeah. So is this sort of here that if you put in hidden units over here, then you're sort of introducing more decision boundaries in the input space. So, for example, if you have a figure, if you have a diagram which is something like this, right? So you can essentially put multiple of these decision boundaries like this, and corresponding to those hidden units, and so each decision boundary will correspond to a single hidden unit, and so you can make any sort of structure in this x1 x2 space. Here I'm sort of saying that it's a continuous function, but yeah, for the XOR gate it's binary. There are 4 possibilities, and you can sort of, so this nonlinear sort of non-monotonic function sort of gets can be understood, if can be made, if you allow the hidden unit and 2 hidden units which correspond to 2 decision boundaries. Right. Now that can sort of make a XOR gate, but how do you learn it? Because the hidden units, because we know that this is how a XOR gate should be, and this is corresponding to a OR, and this corresponds to a NAND. So that's why we could make the hidden units by hand. But how will a neural network, or so these were called perceptrons. This one is called perceptron. Perceptrons or ADLINs, adaptive linear neurons, which learn by this gradient descent method. So how will the perceptrons know what hidden values or what decision boundary the hidden has to take? So that was the problem, and it essentially uh, resulted in this neural network winter, I suppose, from around 1968 to around 1980s. During that time, statistical physics also tried to sort of model the brain from a whole perspective. But one more point that I would like to say is later, around in 1991, Hornick sort of proved that uh, if you have one hidden layer is enough to approximate any function. And you don't need multiple hidden layers. So one hidden layer will be enough to approximate any continuous function, any function. Right. So, well, next part of the story is again around 1949 with Donald Hebb, uh, where in his book Organization of Behavior, he there were multiple great ideas in that book, but what has been used very much in this particular work is this particular phrase: neurons that fire together, wire together. Uh, so this was essentially used in 1982 by Hopfield, but we'll come to that. So first of all, let's appreciate this part first, which is these are essentially perceptrons, where the information is being sent from the input to the output, right? So these are called something called feed forward, because your information is going from the input to the output, and it's not bidirectionally connected. Bidirectional. So these are called particular feed-forward networks. So what Hopfield and others, Hopfield, essentially Hopfield, in the starting sort of took this um, idea that why do we have to put it as feed-forward network? Because here, if you consider a single input-output problem, you can think of it as a pattern, right? So he changed this input-output problem in perceptrons to a problem of storing patterns. So he considered if you have this x comma y tuple, right? You have a particular x vector and you have corresponding particular y output, right? So you have this multiple occurrences, like so you want to store x1 vector, y1, x2 vector, y2, and so on. So these are the uh, states, or these are the yeah. Uh-huh. So this one. So what we're trying to jump from is what feed-forward networks that essentially map input to output, right? So you can take input to output, this mapping, as a particular pattern. So you want to store this input output x vector comma y as a particular pattern, which is x vector y comma y1, right? So all of these are binary units, right? So instead of thinking of this as input and this is output, why don't you take the entire thing as a network, right? So this will correspond to some state S1 vector. And so S1 vector, the network has to know that S1 vector is one of the required configuration. Similarly, S2 vector as one of the required configurations, and so on. So what Amit sort of said is one brilliant step backwards of Hopfield's work. So what he assumed is in the perceptrons, it's directional, right? The edges are directional. It's going from input to output. What Hopfield assumed that why does it have to be directional? Let's just take Wij equal to Wji. So essentially, considering a network of neurons all to all connected, right? And assign an energy function, which is essentially our icing. Oh, everyone's sort of comfortable with icing, right? Where so yeah, so minus half I j not equal to I s I j I j. Let's not call it j. Let's call it w. In the same spirit as that. So that being an input-output problem, Hopfield mapped it to a pattern storage problem. So how do you store binary patterns in a network? And yeah, so one of the prescription that he gave was you want to store this particular pattern. So I'll enumerate them in the superscript, because the subscript is for the particular node. So what Hopfield said is, if you this is the prescription that Hopfield gave, so this essentially gives you an energy function, right, of the entire network. And the objective is the same as that one. How do you learn the weights such that these particular states correspond to the energy minima of the icing, right? So Hopfield said that why don't you store the weights, design the weights in this following way, where Si alpha, the alphas essentially enumerate the patterns that you're trying to store. So this S1, S2, S3, S4, and so on. So here, if you're trying to store these 4 states, you enumerate this thing over those 4 states. So the connection is essentially coming from here. Are we okay till this point? Yeah. Okay. Um, so so this was the prescription given by Hopfield, and it's quite straightforward to see that why this will work out. So if you're aware of the get bra notation, so this one essentially means row vector. This one essentially means a column vector. You see that this is actually can be written like this, right? Is that apparent? Because Si and Wij, Sj all are being summed over. I and J are being summed over, right? So you're sort of something like this, and then your Sj in the end is something like this, and it's something like this, right? So when you're doing this summation, you're essentially multiplying this, and so this will essentially give you, right? So multiplying this and this will give you this, and this will be over here, and you get a dot product, right? So this can also be written in this format. So Ws will essentially give you this one, and your S and Ws will multiply to give you the energy, right? Right. So once you write it in this format, yeah. Sorry, what? The W's are the weights. Yeah. These are not the weights. These are the states. These are the same as the McCulloch neuron uh, nodes. The edges are the weights. So here we had directional weights, right? We had these directional weights, and we were learning these by gradient descent. Here, these are weights. So the weights are the ones which are actually storing the information, or which are essential for learning, right? There we were learning it by gradient descent, like getting to the required weight by gradient descent. Here we are learning the weights by this prescription. With the alpha, Si alpha, Sj alpha, the alphas are essentially correspond to the different stored states. Yeah. That corresponds to one of the stable state. That corresponds to one of the input output problem solution. Correct. Yes, exactly. Like this. All right. Apologies. Yes. Yeah. So I'll just repeat what he said. S vector alpha I essentially corresponds. It means the state at I when the configuration is alpha. Is that correct? Right? That makes sense. So what are we doing over here? We are look at the pairwise correlation across all the states. Now, across all the stable patterns between I and jth node, and then assigning the connection strength according to that. Right? So why does it work? So if you just put it inside this particular prescription, so I can write W like this, right? W equal to sum over alpha. So there are p number of patterns. So goes to S vector p. There are p number of patterns that we want to store. There are p number of configurations, right? S alpha. I suppose when you do ket or bra, it automatically says that it's a vector array. So this can be written like this, right? These two are equivalent. So if you put this W inside here, so it's sum over alpha right? So this is the energy of state S. So energy of state S is given by this. We're clear till now. Now, you see the energy of state S is essentially, you can take out the sum over alpha. Once you take out the sum over alpha, these two collapse into inner product. These two collapse into an inner product. So you have S alpha whole square. So the energy of the system at S vector is essentially inner product of S and the S alphas, the patterns that you're storing, whole square. So when is the energy minimum? When S is S alpha, right? So you see, if one stores the W's as prescribed by Hopfield, which is very simple, right? With simple as in the same essence as Hebb, pairwise correlation, neurons that fire together, wire together, right? Pairwise correlations of the stable states or the patterns that you want to store. Yes, you have a question? Right. You arrive at this particular scenario. So your energy function is defined with the normal easing, and your weights are prescribed by the Hebb learning rule or Hopfield's prescription. And what you arrive at is energy landscape where you have particular areas which corresponds to, this will probably corresponds to like this one, the other one will correspond to this one. So essentially arrive at a scenario where the input output problem is mapped to a pattern. So this is pattern 1, this is pattern 2, and these are the energy attractor basins, right? So that was the key insight, that mapping the input output problem of perceptrons to energy landscape for networks which are generally called recurrent neural networks. Yeah, mostly, yeah. So it can converge to any of the S alphas, or when there are too many S alphas, then there are some things called mixed state. So Hopfield essentially gave this argument. He did and gave this one-shot rule, and hypothesized that you can also have a incremental learning rule, which is of this form, pairwise correlation across the store, or patterns that you want to store. Essentially Hebb's idea, right? Pairwise correlation of the patterns that you want to store. So the delta W, the WIJ can also be modified incrementally. So the thing that Hopfield did was only for McCulloch-Pitts neuron. So your activation profile was a step function. That you're below a certain input and you're off, and you're above a certain input and you're off. Statistical physicists realized that as soon as they introduced this energy function, this entire field became open to statistical physicists, right? So this is something, and he coined. I don't think he coined it, someone else coined it. But this is sort of something called content addressable memory, right? So you start from anywhere close by and it will complete the pattern. So you can imagine if you start with +1 +1 and let this be anything, right? It can be -1 or +1. It will converge to the correct answer, which is +1 +1 -1. So in principle, all sorts of gates can be stored, but without like using perceptron sort of directed edges, you can store it with in the energy landscape. So this the statistical physicists sort of came in the field because like after defining this energy function, they realized this is something similar to what are called spin glasses, some special case of spin glasses, where you have a lot of yeah. So where you have a lot of minima. So in case of, if you consider normal easing, you have this E equal to -12 J, and then you have SI SJ, right? Where J not equal to I. Sum over I and J, right? So here, the number of minimas are essentially 1. The number of patterns that you're storing is essentially 1, which is all up. All down is the like complement, so we just consider all up. So the number of patterns that you're storing is essentially 1. But in case of spin glasses, you allow the J to be any sort of connection, any strength connection. And what they see is it's a very rugged landscape. And so you can have local minimas, and so it can get stuck. And Hopfields is essentially creating another spin glass, but it's making it in such a way that there are particular stable patterns, right? So it's essentially sort of like a particular class of spin glasses, and a lot of statistical physicists sort of got into this idea, and they theoretically showed that there is a particular limit up to which you can store patterns. So if your system size is n, you can store about p equal to alpha n number of patterns, where alpha is somewhere around 0.14. So you can store 14. So if you have 10 neurons, you can store 1. If you have 1,000 neurons, you can store 140 patterns. Did I say the right thing? No, I didn't say the right thing. If you have 1,000 neurons, you can store 140 patterns. Yeah. So this was essentially done full analytically by Amit Goodfriend and Sompolinski around 1985, and they also showed that there is a particular non-zero temperature at which this memory recall, where you're starting at some point and you're recalling and figuring out what is the stable state. This memory recall is optimum, like best. Yeah. What was your question? Uh-huh. This essentially tells you that the number of patterns that so if you have a system of size 1,000, you can store alpha into 1,000 number of patterns. So alpha into 1,000 number of stable configurations or stable patterns that you can store. That's what alpha is. So P is the total number of patterns that you can store. Alpha n is the relation to the total number of units that you have. What do you mean orthogonal? So what? So this is something that happens in is your basin actually looks something like this. So this might be your state S1, and this might be your state S2. What ends up happening if you store more than 3 patterns? What ends up happening is you have these mixed states, which are essentially part of the pattern will be of S1 vector, another part of the pattern will be of S2 vector. So this will be sort of like a chimeric state, where a part of it is resembling S1 vector, another part resembles S2 vector. So if you're close enough, right? If you're close enough, it will always go to the, so here. So if you're here, then you'll be stuck, and then it's how is it defined, the boundary or the neighborhood? How is it defined? You're close by, and you go to the stable state. So if you define something like +1 -1, and I want the state to go to +1 +1 -1, that won't happen, right? Because you're too close to the other state. So it will go to that other state. So you have to be close enough to your stable state, or your whichever input output or pattern you want to be. You have to be sufficiently close. Yes. Yeah. So locally, that is the least energy state. So over here, everything else is high, right? This part is the only place where it's low. So if it's essentially pattern completion. This is also a pattern completion problem, right? You are giving inputs, you want to find the output. So that is sort of like what's happening here. You're giving the input, which is sort of close by, but it's not exactly at the output, and it sort of finds the pattern. So it essentially gives you the output. Did I make any sense? It might have same energy, it might not have same energy, but they are locally stable. So if you're here, if you're somewhere here, it will definitely not go here. It will go to its local energy minima. So they're locally stable, but globally there are multiple attractors. It has to be like your initial starting configuration has to be near the basin of attraction. So your input has to be well defined to get an output. Yes.
So this E can give essentially like if you put any S vector,
Yeah.
this can give you one value of energy.
Yes.
So what I'm asking for these particular P states, which we want to store, will the energy is the absolute minimum, or there are some other S which can give you lowest values than the required P or desired P?
Uh, yeah. So when you're giving a state S, right, then you're essentially your initial condition is somewhere close to an attractor when you're giving it an S vector, right? So it will trickle down to the closest minima. But it does not mean that the others are not minima. They are also minimas. They might be deeper, they might be same, they might be slightly high, but they are also minimas. It's just that the system has sort of, I don't want to use this word because it has a lot of connotations, like the ergodicity is broken. So the if at T equal to 0, if your temperature is 0, then the ensemble average is not the time average. So if you're starting at this state, it will not be able to jump out. It will just stay here. But that doesn't mean that there are no other minimas. There are other minimas, but it cannot jump out. So when you're giving it a state, it's actually somewhere close to the basin of one of the stable patterns. Does it make sense? Minimums deep enough that are not part of the patterns that we're storing. You can. So that's where this limit comes. If you're storing more number of minimas, like more number of patterns than larger than this calculated limit, then you will have these spurious minimas that pop up. And then it can give you erroneous results or erroneous patterns that you didn't want to store in the first hand. Right? Yeah, yeah. If it's very far away, it will be stuck. But if so, one thing that people can do is something called simulated annealing. So, if you start with a higher temperature, so if you're at a higher temperature, since it's low, since these basins are smaller, not very deep, if you start with a higher temperature, to sort of like wash it out. So this will correspond to at a high temperature something like. So you can start with the high temperature and then gradually lower it. So you start with this high temperature over here, it will probably trickle down over here, and then you lower T, and so you start with the system, the state over here, right? In this case, it will probably go here. But if you start with a high T, then these metastable states are, sorry, mixed states are not there. And so it starts trickling down, but because of the high T, it will sort of, be like very, like not reach the absolute minima. But then you lower T, and so when you lower T, these again reappear, but your state has already gotten inside, right? So it will gradually trickle down. So you've sort of escaped the the mixed state by starting from a higher T and gradually lowering it. Similar, yeah. So in most cases, you don't need this simulated annealing. It's pretty stable, well defined. Right. Uh, any question? Okay. Yeah. So I suppose I could drive the point forward that the effort started from a feed-forward networks where they were trying to do input-output mapping with directed networks and how to make networks like that. To Hopfield's contribution was to forget about the directed part, think of the output input-output problem as a pattern storing problem. And so how do you store patterns in a system of networks? And so he essentially came up with a way where you learn the weights or where you adjust, like put the weights such that those patterns, those input output problems essentially minimize. Right. So, but the only thing was he used, the only thing as in a bit far away from normal setting is that he used temperature equal to 0. So, binary threshold unit. Uh, sorry, I mean a step function. Yeah, yeah.
So essentially that you have written towards the end like E is a function of S vector. Yeah. And what is your looks like what are the SP?
So this will correspond to S1. This will correspond to, sorry, S2.
So what is the input like? Which are the desired input? Uh,
So these are sort of the desired inputs, right? So this might correspond to a state which is +1, +1, +1, corresponding to AND. So S11, so S1 is this, S2, you can't see. You can see. S2 is this, and S3 is this. So corresponding to this, what is this? AND? I don't know. So corresponding to the AND problem, this will be one of the input output problem or the pattern. This might correspond to the other one, which is +1, -1, -1.
so essentially what I ask is if you increase the S vector, say I have like because essentially for n
Yes, yes, yes.
so towards the end towards the end is there any larger deal?
Oh, no, no, no.
So towards the end is there any larger deal? Our input range.
What do you mean by particular section?
So where like S is place where the input. What I am asking essentially to increase that S vector. That is
And look at the rest of the space,
considering all 2 to the power n states.
right?
So is there any larger diffs?
No, no. It won't be because if you consider a state which is far, so this is the state space, like all the S possible. There are 2 to the power n states in this space. Okay, so this is sort of populated by these basins of attraction. So these are where the minimas are located, and
These
they
are
are
the global minima, right? I mean, absolute minimum. I mean, these are the ground states of that energy, that Hamiltonian. That's
I don't know if I can use the word ground state, but if like these are local dips in the energy landscape. All these other places are far above than the energy landscape. So there is no idea of boundary, right, in this state space because you like it's connected.
so these are the lowest energy states.
These are the lowest energy states. Yeah. Sorry, was I not able to answer your question? Oh, you know, okay, okay, all right. Yeah, yeah. Right. So, yeah, Hopfield sort of did it with temperature equal to 0 or step function. So, what the first thing that one can do is assign a probability for a particular state, probability of S vector. So once you allow StatMech to go in, you can assign a probability for the state vector S, right? So e to the power minus, I'm considering beta to be 1, e S vector by z, where z is the normalization or partition function, whatever you want to call it. Right? So this is one can essentially start with when you think of this problem in terms of StatMed. So now the Boltzmann probability. So the Boltzmann factor, which is essentially what is the probability of a state 1 S1 vector compared to the S2 vector. This can be written and you can essentially get something like E of S1 vector minus E of S2 vector. Is this clear what I did? Because the Z gets cancelled out and you have only ES vector, ES1 vector and ES2 vector, right? So probability of S1 vector by probability of S2 vector equal to e to the power minus ES1 vector minus ES2 vector. So now let us just consider a single thing, which is I'm trying to, so the difference between S1 vector and S2 vector, consider the difference between S1 vector and S2 vector as a single spin flip, spin difference. Difference between S1 and S2 is essentially a spin flip at ith position. Spin difference. Right? So what it means is probability of, let's say, Si is equal to plus 1 by probability of Si is equal to minus 1 is essentially, so these are, all the others are same. All the other spins are of the same are aligning in the same direction. It's just the ith position spin is different. All right. Then we can write this as, so ES1 vector will have all the contribution of Wij, Sj, right? All of them will cancel out except the Si ones. So Si, Wij, Sj. So only the Si one will stay, right? Because all the others are same. So if you consider Sk, Wkj, Sj, then all the others will cancel out because the only difference between these two states are the spin at ith position. So we can cancel them out and then put Si is equal to 1. Right? We're E of S1 vector and S1 vector corresponds to this. Yeah. Certainly. Like, Boltzmann. So here we were doing, so in an Ising system or any system, how do you define the state of, not define, like, what's the probability of occupancy of a particular state? That's given by the Boltzmann probability, right? So here we were not using probabilities at all. So now what I'm trying to do is describe this entire energy landscape in terms of, like, what's the probability of the system being in one of the states.
Can change times.
If you do a time average, you will see that there's a peak. So it will obviously have some fluctuations, but you'll see that the peak is at the stable state. So in this case, in this threshold, like in this step function, right, if you plot the time average, you will have a delta function at the stable point, right? So what I'm doing is I'm allowing temperature to get in the game. So instead of a delta function, you sort of get a spread, but the peak of the spread will essentially be at the stable state. Does that?
In case of
In case of Hopfield, he didn't consider temperature. Temperature was set to 0. So E of S1 vector, right? And all the others are same. S1 vector and S2 vector differ only at the ith position. So I'll be left with, so E, let me just write the energy so that I don't make any silly mistake. Right? So here my SI is plus 1, right? So minus Wi j Sj sum over j. Right? This is my energy of S1 vector. Minus of, oh, there's a minus over here, then there's a minus coming from the energy, and there's a minus one of the spin, right? This was spin up, this is spin down. So sum over j, let me do it like this, sum over j, wij, si is minus 1, sj. So this essentially gives you probability of Si equal to plus 1 by probability of Si equal to minus 1 is equal to e to the power, oh, there's a half. I missed the factor of, there's a factor of half, right? Right. So this minus minus cancels out, and then you have a minus left here also, you have a minus, and the minus here cancel out, right? So e to the power sum over I, sum over j, wij, sj, right? So what is the probability of Si? So now what I'm going to do is I'm going to add 1 and divide. Flip it. So probability of Si equal to plus 1 by probability of Si is equal to minus 1 plus 1 is equal to e to the power sum over j, wij, sj plus 1. And now you see, so you flip it, and so p of Si minus 1 goes up here, and so I'll just write it down so that it's becomes obvious. This is equal to 1, right? This term is equal to 1 because this is what's the at state I, by p of Si equal to minus 1 is equal to this term. Now this term is equal to 1. So this essentially becomes 1 by p Si equal to minus 1, which I can essentially, so 1 by p Si equal to minus 1. And so you see what I get is p of Si equal to minus 1 is equal to 1 by this term, which is essentially the sigmoid, sum over j, wij, sj. So you see how naturally once you introduce the Boltzmann factor, it naturally takes the, takes this step function into this sigmoid. So probability of Si equal to minus 1 is essentially given by a sigmoid, right? And well, this was the first, this is one of the first things that you can do, and we'll probably take on after this point in the next talk. Which paper? This derivation is self. This derivation is self. You can read maybe Hinton Sejnowski, 1983. I can't cooperative computing or something it's called. I can't remember the name. Analyzing cooperative computing. Yeah. Oh yeah, Hertz, Krog, and Palmer is a. But did they come? Yeah. Why did I take it? Yeah, I mean, so this was probability of a particular state, right? So I wanted to arrive at what is the probability of a particular spin flip. So, at a particular position, what is the probability of it changing its state, or what's the ratio of the probabilities of, it being up or it being down? No, here I'm not thinking in terms of input anymore. Here it's more like you have the probability of having a state S vector, right? So in case of these systems, Hamiltonian systems, if I'm not correct, if I'm not wrong, your probability of having a state S1 vector and S2 vector is essentially the difference between their energies, right? So I can take that idea and sort of say that I have two states who differ only at a single spin. Then it will tell me, it will essentially tell me if the state wants to, what's the probability with which that particular spin wants to be up and it wants to be down, right? So it will give me the probability of it being up or down. So that essentially tells me, will it be on based on a certain amount of input or will it be off? Does that clear your question or did I confuse you? It's not. It's called. So the idea is the state. The probability of occupying a particular state is dependent only on the energy, right? So what is the? Uh, it's not a step. I can sort of tell you this that it's essentially if you consider this point and you consider this point. If you consider these 2 points, what's the probability of occupancy of these two? What's the ratio of probability of occupancy between these 2 points? That's what this is. So what it essentially shows you, the ratio of probability of these 2 points, the occupancy of these 2 points, is related to the energy difference between the states at these 2 points.
If the other state has a lower energy, then there is a finite probability. If the other state has a higher energy, essentially it is a lower probability. Right? So essentially, for a finite temperature, there is some probability that you can actually also take steps which will increase your energy. So you can jump over, you know, so to say, the hills from one valley to another with a particular probability. Yeah. So you'd say that the bigger the energy gap, so the bigger the hill, the probability is lower. Right?
Yeah, we will use this in neural networks. You need temperature, non-zero temperature. If it's zero, then it will get stuck in certain places. Well, if you use very high temperature, obviously the entire landscape will be flat. So you have an optimum temperature. The optimum temperature is non-zero and it's not infinite. So it's somewhere in between.